We are going to cover section 1.3, complex numbers, and we're going to start this section by talking about some basic concepts of complex numbers. First, the imaginary unit I. I equals the square root of -1, and therefore I squared equals -1. And we will refer to this definition of the imaginary unit throughout this section. The next thing that we're going to talk about is the definition for a complex number. And if A and B are real numbers, then any number of the form A plus BI is a complex number. In the complex number A plus BI, A is the real part and BI is the imaginary part. Okay, so again, your blanks, A is the real part and B is the imaginary part. The expression is square root of -A. If A is greater than 0, then the square root of -A equals I square root of A. We will start with example 1 using the fact that the expression of the square root of -A equals I square root of A. So we're going to write these square roots using this definition. So if you look at part A in example 1, we have I'm going to move this up. We have the square root of -16. So we want to start out by using again this definition that we just talked about with the square root of -A and rewrite this as I square root of 16. So once you pull out your -1 as I on the outside of the square root, you break down your square root just like you would any other square root. If it is a perfect square, then you take the square root of that. If it has to be broken down into two separate radicals and simplified, then you do that as well. So for the square root of 16, the square root of 16 is 4. So this answer would be 4i. So your final answer for part A would be 4i. If we look at part B, we'll do the same thing. We will pull out our -1 first. So that will be I square root of 70. I square root of 70. 70 is not a perfect square. And so the next thing we want to look at is, can 70 be broken down into a perfect square and a number that is not a perfect square? And it cannot be. So for part B, your final answer will be I square root of 70. For part C, we'll start the same way, and that will be I square root of 48. And then again, 48 is not a perfect square, but we can break 48 down into two numbers, one a perfect square and one number that is not a perfect square. And the easiest way to do this is to find the largest perfect square that will divide into 48. So for 48, that will be the square root of 16 times the square root of 3. So again, 16 is a perfect square and 3 is not. So the number that is a perfect square, you will take the square root of that number. So the square root of 16 is 4. That gives you 4i on the outside. And since you cannot take the square root of 3 and that could not be broken down, you will leave that underneath your radical, making your final answer 4i times the square root of 3. 4i times the square root of 3. All right, now we are going to look at our next example. And before we do that, then we're going to get a definition on the top of the next page. All right, so we're talking about, again, operations with your complex numbers. So we're going to multiply, divide, add, and subtract complex number. So it says, when working with negative radicands, use the definition, the square root of negative a equals I square root of a, before using any of the other rules for radicals. So just like we did in example 1, you want to use this definition first, rewriting the square root of negative a as I square root of a, and then you can proceed with multiplying, dividing, adding or subtracting, depending on what operation you are doing. So on example 2, part A, our first part says the square root of negative 7 times the square root of negative 7. So again, you want to start by rewriting this as I square root of 7 times I square root of 7. And once you rewrite that with your I on the outside of the radical, then you can multiply just like you typically would with radicals. So I times I is I squared, and the square root of 7 times the square root of 7 will be the square root of 49, but that is just 7. So remember that anytime you multiply a radical times itself, your radical goes away. Now, go back to your definition that we learned at the very beginning, and that is that I squared equals negative 1. So this is equal to negative 7. Negative 7. So your final answer for part A is negative 7. And again, if you'll go back to what I just said, the square root of negative 7 times the square root of negative 7, those are both the same. So we really knew from the beginning that that answer was going to be negative 7. However, on part B, since they are different, you have the square root of negative 6 under one radical and negative 10 under the other radical, then it's not going to be one of those numbers. So you will have to go through the steps that we just went through in part A. So again, use your definition, and that will give us I square root of 6 times I square root of 10. And once you have those i's on the outside of your radical, then you can multiply your according to your radical rules. So I times I is I squared, and the square root of 6 times the square root of 10 is the square root of 60. The square root of 60. Now, I squared will be negative 1, so now you have negative square root of 60. And 60 is not a perfect square, but 60 can be broken down. So you want to break 60 down into a number that is a perfect square and a number that is not a perfect square. So that will give us negative 1 times the square root of 4 times the square root of 15. 4 being your perfect square and 15 being your number that is not a perfect square. So when we take the square root of 4, we get 2. So on the outside you have negative 2. And since 15 is not a perfect square, then you will leave that 15 underneath the radical, making your final answer negative 2 square root of 15. Alright, on part C, we're going to move from multiplying radicals with complex radicals to dividing. I'm going to move this up. And if we look at part C, again, you will start these the same way. So that is I square root of 20 divided by I square root of 2. I square root of 20 over I square root of 2. Now your i's will cancel, and then since you have square root of 20 over square root of 2, your radical rules say that you can divide 20 and 2, and that will give you the square root of 10. The square root of 10. Now 10 is not a perfect square, and 10 cannot be broken down into a perfect square and a number that is not a perfect square. So your final answer for part C is the square root of 10. We will work part D similarly. And so again, we will start with I square root of 48. There is not a negative underneath the radical on the bottom, so this will stay the square root of 24. There's not an I on the bottom, and your I is not squared, so you're just going to leave that for right now. So you have the square root of 48 divided by the square root of 24, so that is I square root of 2. I square root of 2. Again, 2 is not a perfect square, and 2 cannot be broken down, so your final answer is I square root of 2. So when you are multiplying or dividing negative radicands, then you want to make sure that you use your definition of pulling out that I first, of rewriting that, and then you proceed using your rules for radicals. The next thing that we're going to talk about in example 3, we're going to simplify a quotient involving the square root of negative a, so that will be in standard form a plus bi. So if you look at example 3, then you will start by simplifying what is underneath the radical, just like we have done in these other examples. And then you will be able to reduce or simplify so that that is in standard form. So if you look at the square root of negative 128, the first thing that you want to do is to pull out your I. Again, just like what we did on example 2. Once you have your I on the outside of the radical, then you want to look at your square root of 128 and see, can that be simplified? It is not a perfect square, but it can be broken down into a number that is a perfect square and a number that is not a perfect square. And that will be the square root of 64 times the square root of 2. So that gives us negative 8 plus I times the square root of 64 times the square root of 2. Again, since your 64 is your perfect square, then you take the square root of your 64. So that gives us negative 8 plus 8i times the square root of 2 over 4. Now, your square root of 2 is that's not a perfect square, and it cannot be broken down any further. So as far as breaking down your square root of 128, you are done with that part of the problem. However, keep in mind that when you are simplifying complex numbers so they're in standard form, you reduce these very similar to how you would reduce a fraction. But keep in mind, you have 3 things that you have to consider and not just 2. So to be able to reduce a complex number into standard form, it has to be a common factor between all 3 of these numbers, not just 2. So since we have 8, 8, and 4, then 4 will go into all 3 of these. So when we reduce this, 4 will go into 8 2 times, so that gives me negative 2, plus 4 will go into 8 2 times, so that gives me 2i square root of 2, and 4 will go into 4 1 time. But since that 1 is understood on the bottom, you do not have to write that. So your final answer is negative 2 plus 2i times the square root of 2. So again, your final answer is negative 2 plus 2i times the square root of 2. So don't forget that on these problems, like example 3, you will first start by simplifying your radical, and then you will reduce your fraction if it can be reduced. Alright, now we are going to look at, I'm going to flip the page, and we're going to talk about adding and subtracting complex numbers. Adding and subtracting complex numbers. Now, when you add or subtract complex numbers, then it is very similar to combining like terms, so to speak. So to add or subtract complex numbers, as we fill in the blank, then you add or subtract the real parts and add or subtract the imaginary parts. So you will add or subtract the numbers that do not have i's, which are your real parts, and then you will add or subtract the imaginary parts, which are the parts that do have i's. So again, it is very similar to simply combining, adding or subtracting polynomials, but in this case you have complex numbers with those i's. So if you look at example 4 on part A, then you will see that we have 3 minus 4i plus negative 2 plus 6i. So again, you're going to add your real parts, which is 3 plus negative 2, and then you're going to add your imaginary parts, which is negative 4i plus 6i. So when you add 3 plus negative 2, you get 1. And when you add negative 4i plus 6i, you get 2i. So when you combine, or when you add 3 minus 4i plus negative 2 plus 6i, your final answer is 1 plus 2i. Now we can't take this any further because 1 is the real part and 2i is the imaginary part. Just like if that were 1 and say 2x, you could not combine those because those are not like terms. Same principle applies when we're dealing with complex numbers. You can add those real parts and you can add those imaginary parts, but you can't add a real and an imaginary part. So if you look at part B, now we are subtracting, and we have negative 4 plus 3i minus, in parentheses, 6 minus 7i. So the best thing to do to keep from making careless errors is to remember that this negative is the same as a negative 1, and so if you distribute that through your parentheses and rewrite your expression, then you can work it just like you did when we were adding in part A. So we have negative 4 plus 3i minus 6 plus 7i. Negative 4 plus 3i minus 6 plus 7i. Now you can do the exact same thing that we did in part A, and that is combine your real parts and combine your imaginary parts. So we have negative 4 minus 6, negative 10, and 3i plus 7i is 10i. So your final answer for part B is negative 10 plus 10i. If you will look down at example 5, the next operation we're going to talk about with complex numbers is multiplying complex numbers. And you'll see here in your gray box that for complex numbers A plus BI and C plus DI, you can use the full method. So again, just like we multiplied polynomials with x's and y's and so forth and so on, you can multiply these complex numbers the same way. Just keep in mind that when you do this and you multiply those two imaginary parts, you will get an I squared. And like we talked about at the beginning of this section, I squared equals negative 1. So you'll notice here written out when you full your A plus BI times your C plus DI, this last term where you get BDI squared, that changes to negative BD because your I squared is equal to negative 1. Alright, so let's look at example 5. And in example 5, your part A, you have 2 minus 3i times 3 plus 4i. So again, we're going to full, keeping in mind that full is first, outer, inner, last. First, outer, inner, last. So 2 times 3 is going to give us 6. And 2 times 4i is plus 8i. Negative 3i times 3 is negative 9i. And negative 3i times 4i is negative 12i squared. Now, from this point forward, you will simply combine like terms and then simplify completely. So your 8i minus 9i will be negative 1i, and your I squared, sorry about that, your I squared is the same as negative 1. So negative 12 times negative 1 will be a positive 12. So we have 6 minus I plus 12. Again, you have to completely simplify. So 6 plus 12 are both real parts. So 6 plus 12 is 18. So you have 18 minus I, and that is your final answer for part A. If you will look at part B, you will do this the same way, but notice that you have 4 plus 3i squared. Now, you will not simply square 4 and square 3i and then be done. Keep in mind that when we square a number, you are multiplying it times itself. So if that was 2 squared, then we would be saying 2 times 2. So it's the same way with 4 plus 3i squared. You will need to say 4 plus 3i times 4 plus 3i. So once you write this down twice, because again, 4 plus 3i squared is the same as 4 plus 3i times 4 plus 3i, then you will pull this the same way that we did part A. First, outer, inner, last. So 4 times 4 is 16, and 4 times 3i is 12i. 3i times 4 is also 12i, and 3i times 3i is plus 9i squared. Combine your like terms, 12i, 12i, and you get 16 plus 24i. I squared is the same as negative 1. Negative 1 times 9 is negative 9. So now we have 16 plus 24i minus 9. Combine your like terms, 16 minus 9. And our final answer is 7 plus 24i. 7 plus 24i. Alright, if you look at part C, we're going to do the same thing again. So we're going to start out by fulling. So 6 times 6 is 36. 6 times negative 5i is negative 30i. 5i times 6 is plus 30i. And 5i times negative 5i is negative 25i squared. Notice that your terms in the middle, negative 30i plus 30i, cancel. So we're left with 36, and I squared again is the same as negative 1, and negative 1 times negative 25 is plus 25. So now we have 36 plus 25, and your answer is 61. So you do not have an imaginary part for your answer in part C. So you can write this as 61, or to write this in standard form, then you would write 61 plus 0i. Again, 61 being your real part, and since we do not have an imaginary part, 0 is your B. So you can write this as 61, or if My Labs Plus asks you to write this in standard form, it would be 61 plus 0i. Alright, that is it for multiplying complex numbers. So the next thing that we're going to talk about in example 6 is dividing complex numbers. Before we talk about dividing complex numbers, then we need to talk about the conjugate. Okay, so you'll look on the top of your next page, all right, where it talks about the property of complex conjugates. Okay? For real numbers, a plus b, if we have a plus bi times a minus bi, then that equals a squared plus b squared, and that is the property for complex conjugates. Now, but let's talk about what a conjugate is. If you'll notice, if you have a plus bi, then your conjugate is a minus bi. So your conjugate is simply the same numbers, but your sign in the middle changes. So if this would have been a minus bi, then the conjugate would be a plus bi. So remember, your a stays the same, your bi stays the same, but what changes is that sign in the middle. And the product of a complex number and its conjugate is always a real number. So you'll notice that when we multiplied those conjugates, we got a squared plus b squared. There's no longer an imaginary part. So to find a quotient of two complex numbers in standard form, we multiply both the numerator and the denominator by the complex conjugate. By the complex conjugate of the denominator. So as we look at example 6 and we talk about dividing complex numbers, then the first thing you're going to do is look at the denominator, and you're going to divide the numerator and the denominator by the conjugate of the denominator. And when you simplify, then you will no longer have an imaginary number or an imaginary part in the denominator. So let's look at example 6, part A. We have 3 plus 2i. 3 plus 2i divided by 5 minus I. So if you'll focus on that denominator, we have 5 minus I. Then the conjugate of 5 minus I is going to be 5 plus I. So we are going to multiply the numerator times 5 plus I, and we are also going to multiply the denominator times 5 plus I. Now, you are going to fool both the numerator and the denominator. So on the top, you're going to say 3 plus 5 is 15, and 3 times I is 3i. 2i times 5 is 10i, and 2i times I is 2i squared. All divided by, now on the bottom you are going to fool your 5 minus I times your 5 plus I, which is its conjugate, but keep in mind the property of complex conjugates says that those middle terms cancel. And so essentially all you have to do is multiply your A times A and your BI times your BI, because those middle terms you already know are going to cancel. So 5 times 5 is 25, and negative I times a positive I is negative I squared. So once you fold the top and then you use that property of complex conjugates on the bottom, then you will simplify just like we've been doing on these other operations of complex numbers. So in the top, your 3i plus 10i is 13i. I squared is the same as negative 1, so that is negative 2. All divided by I squared, again, is negative 1, making that 25 plus 1. So we have 26 in the denominator. And in the numerator, 15 minus 2. Again, we're continuing by combining like terms. We get 13 plus 13i divided by 26. Now remember, when we simplified a complex quotient, then we need to look and see if we can reduce that fraction. We have 13, 13, and 26. 13 will go into all three of those, so we can reduce. 13 will go into 13 once. It'll go into 13 once. It'll go into 26 2 times. Now you know that this 1 right here is understood. You do not have to write that. And the way you are going to see this written in MyLabs Plus is going to be separated. So that will be 1/2 plus I divided by 2. 1/2 plus I divided by 2. Alright, for part B, we have 3 divided by I. So your conjugate works the same way. If we have I, then the conjugate for I is just the opposite of the positive, and that will be a negative. So we will multiply the top by negative I, and we will also multiply the bottom times negative I. And then you will proceed with this the same way that we did part A. So 3 times negative I will be negative 3I. I times negative I will be negative I squared. We cannot simplify the numerator. That will stay negative 3I, but on the bottom, I squared is the same as negative 1. So negative times a negative 1 is a positive 1. Again, we do not have to write that 1 on the bottom, so this is the same as negative 3I. Negative 3I. Or if you will think back to the last example that we worked, and we talked about writing this in standard form, if you rewrote negative 3I in standard form, your negative 3I is your imaginary part, but your real part would be 0. So we would write this as 0 minus 3I if they asked you to write this in standard form. Alright, now this does conclude the section on complex numbers. However, I do want to point out that we have a note down here that says you can also work example 5 and example 6 in your calculator. So I'm going to show you how to do one of each of those in your calculator. And then that will conclude this section, and then you can try your exercises 17, 21, 23, 27, 31, 41, 43, 45, 51, and 69 from your ebook as additional practice before you begin your homework exercises in MyLabs Plus. So I'm going to move this sheet, bring my calculator here, and I'm going to look back at example 5 part A. Again, I'm not going to rework all of these, but I am going to work one part from example 5 and one part from example 6, so you can see that you can do these in your calculator. That's very important that you use parentheses, or you will not get the correct answer. So if we look at part A, we have parentheses 2 minus 3, and your I is right here, and so you have to use your second button, second I, close your parentheses, open your parentheses again, 3 plus 4I, close your parentheses, and enter. And we have 18 minus I. And if you will notice on your example 5 part A, that is the solution that we got, 18 minus I. Alright, I'm going to clear that, and then I'm going to look at example 6 part A. Example 6 part A. So again, you want to put your numerator in parentheses and your denominator in parentheses. That is very important for you to get the correct answer. So in example 6 part A, we have parentheses 3 plus 2I, close your parentheses, divided by, open your parentheses, 5 minus I. Hit enter, and you'll notice that we get 0.5 plus 0.5I. You do not want to enter this as a decimal answer. You probably already know that 0.5 is the same as 1/2. But if you got a decimal that you did not know right off the top of your head, you can simply hit math, and you'll see that it is highlighted on fraction. Hit enter, enter, and it will change your decimals to a fraction. And so you see that you get 1/2 plus 1/2I, and that is the solution that we got for example 6 part A when we worked that by hand. So again, You know how to work these by hand, but you can also work these or check your answers using the calculator for problems like example 5 and example 6. So hopefully this will help you. That does conclude our section 1.3 on complex numbers. Don't forget your now try exercises in your ebook before you begin your homework exercises.